Hi, everyone. Okay, now, is there any question about the previous sessions? Please feel free to ask. What about any question about the assignment?
Yeah, I think I'm just misunderstanding it, but when I was reading
Sorry, could you
it
please repeat? Could you please repeat? Hi.
when I was reading the assignment, my first impression for question 2 is that there's a fixed $3 loss of profit in total means that the profit of the overall problem is fixed at -3. I'm assuming that's incorrect, but I'd like some clarification on how that would actually look in the problem.
So the cost or the objective function that you have when we have a loss, a fixed $3 loss, what does it mean? It means that you should apply it in the cost function, right, as a constant. Is that correct?
Okay, so that's a constant rather than a constraint on the problem.
It's a constant, and as the objective function is the profit, right? Total profit. Therefore, you can include it in your cost or in your objective function. And if you remember, we talked about how to deal with the constants in the cost function in the lectures. Do you remember that?
I was just confused about the wording of it. It seemed weird to me. That's all. Okay, thanks.
Yeah, okay. Thank you. So yeah, whenever, even including exam, assignments, wherever you think that there is an ambiguity, please let me know. Please don't hold it. Ask and let it be clear. And yeah, also, so you can ask your questions now. Yes.
Hi, I actually want to just confirm that for the assignment, we need to do it on the pen and paper, and we can just upload the assignment on the Dropbox.
Yes, exactly. You can write it in your paper, and I suggest, this is just a suggestion, you can use Cam Scanner on your phone. You can just install Cam Scanner and then scan by Cam Scanner from your phone, because when you take picture, it might not be visible very well. So if you use Cam Scanner, I think it will be very, and use magic color in the Cam Scanner, it will be like you are scanning that. So I think that would be best. Yes, no problem. Thanks.
Sorry.
Yes.
Does it have to be like handwritten?
Sorry, I couldn't hear you clearly. What?
Does it have to be handwritten, like the assignment? Does it have to be like handwritten on paper, or
the code are you talking about?
Like the assignment.
The assignment, yes, you can write it, except the code. For the code part, please, I will explain for the code what to do. But for the rest of the assignment, just write on the using pen on the paper, and then afterwards at the end take picture and use Cam Scanner. This is my suggestion in order to have a very good scan of your paper.
All right, thank you.
No problem. For the coding question, my suggestion is that you code in Python and then put a screen, put your code in a document like the Word document or Google document, whatever you want, and then print it as a PDF and attach it to your Cam scanned solutions. And also in the document that you're putting your code, try to explain a bit, not too much, a bit what you're doing in your code. So open a Word document or Google document, write, put your code in a box in that, and then explain a bit what you have done, and then attach it at the end to the PDF of your other solutions. So, and upload the whole PDF. If you can also upload the .py or or if it is Jupyter Notebook, your Jupyter Notebook file, in addition to the PDF, that would be best. So the whole solution as a PDF, including your code and explanation, and one .py or the Jupyter Notebook file, that would be best. So anything unclear about assignment? And by the way, I have tried to make the assignment straightforward, and I'll try to make the exam also straightforward, so you don't need to worry about that. I think you have seen examples of what you have in assignment in the lectures. So if you read the lectures carefully and understand them, I think it will be an easy assignment for you. But feel free to ask me questions either here or off class. You can ask in the Teams group chat, Q&A chat, group chat. I'm not sure why people are not asking questions. I'm not sure whether it's a good sign or a bad sign. But feel free to
Maybe
ask
there
your
will be
questions.
more questions around after the assignment starts. Before doing the assignment.
Yeah, I understand. But don't push it to the last moment, please. I think it would be easier for you to do it gradually. And if you have any question, ask. Don't push it to the last moment. Also, please don't submit in the last moment, because I'm not sure about the system. I have put it 11:59. I hope it's EST time zone. I'm not sure, but as we are, I think University of Guelph is in EST time zone. I think by default it's EST time zone. If not, I'll try to fix it. But even if it is EST, its deadline, it doesn't let me set the seconds of the deadline. So I have set 11:59. I'm not sure what second. Is it 11:59:59 or is it 11:59:01 or 00? So be careful. Don't submit in the very, very last moment. I'm not sure about the system. Okay, so we talked about the assignments, and I think in the next session, I will briefly talk about the project. I think next session is a good time to start talking about the project. Of course, it will be team-wise, but how many people in each team, also what to do, and how to let me know your teams. And I will talk about the details in the next session. So I think, yeah, that's good. If any other question before we start? No? Okay, great. Sorry, there is in chat. Sorry if we are new in Python. Ali Riza has asked, could you please extend the deadline? Ali Riza, sorry, we really can't extend the deadline for several reasons. I think the biggest reason is that I will put the key response to course links, so you can study better for the exam, have some reference responses. Therefore, I suggest please try to submit before the deadline. And experience has shown that if we change the deadline frequently, people will be frustrated. So that's why it's better not to change the deadline. This is a deadline, so everyone knows their schedule, and try to meet the deadline. About being new in Python, don't worry about that. So I think Python is very easy. You can learn it in a few days, even in one day. You can do that. If you know any other language, even if you know MATLAB or other languages, I think you already know the concepts of coding, so you don't need to worry about that. Just I think it will take you at most one day to learn Python. And what to do, the best way for me to learn Python and these things is YouTube. On YouTube, search Python tutorial. There are some several hour sessions on YouTube. You can learn anything on YouTube, and I think YouTube is a very good source. So just search Python tutorial or Python tutorial for beginners, and it will come. And just by several sessions, put it in the speed 2. So with speed 2, you can watch very fast and you can learn very fast, and then try to practice a bit, and I think you will know Python. And this question is not hard. This question is not hard. It's just a while loop and some if-else conditions and these things. It's very easy. Also, please note that I say this from now so you can get ready for that. Don't be shocked. I think I will teach you that. I'm not expecting you to know that. I will briefly tell you how to work with that, but we will have a question in assignment 2. We will have one coding question about using the neural network for optimization. And it will be several lines of code using we will learn libraries. And why do we do that? Because your second assignment, so this first assignment was about preliminaries and cake and linear programming, integer linear programming sensitivity analysis. Your second assignment will be about first order optimization. One of the nowadays very important and famous first order optimization methods is neural network, right? It will also cover that a bit. And I will let you know how to use PyTorch, so you don't need to worry about that. But at the end of the semester, you will see that you have learned a lot. You have learned a lot in different areas of optimization. So this will be worth it. And also, your third assignment will be about second order optimization and Newton's method and these things. So we will go over these things and you will learn a lot, and I'm sure you will enjoy that. So this is okay. Any other question? No? Okay, great. So let me share screen. Okay, great. So one thing that I want to let you know before continuing is that in Big M method, you might be wondering, so recall the examples that we covered. We covered 2 examples in Big M method. One of them is this, and you might be wondering how, so if you see in the 0, we have minus 150 M, right? Like here. Then by elementary row calculations, the M is cancelled somehow. You might be wondering, what if it doesn't get cancelled? Yes, in some of the steps, it might not get cancelled, but usually at the end, you will not have M in the 0. So it's either because if we have M in the 0, we might have minus M, which will be minus very infinity, or we might have M, which will be a huge number, a huge positive number, and explode the objective function. Therefore, in both cases, it's not desirable. So usually M gets cancelled. In some cases, M doesn't get cancelled. Usually in those cases, at least one of the artificial variables is not 0 at the end. So we reach a case that all of these values in the 0 will be non-negative, and suddenly you'll see that by the way, we have some M here, and also the some of the additional variables are non-zero. So at least one of these basic variables become additional variable. So in these cases, usually the optimization problem is infeasible. Please note that when we have a feasible solution in optimization, all of the additional variables that we use in the Big M method should eventually become 0. Otherwise, in other words, the additional variables should become non-basic variables. Why? Because we added additional variables, multiplied M in the cost function. Of course, they should become 0 to cancel the effect of M. Even if they are tiny, they might explode the cost function, right? Therefore, at the end, additional variables must become 0. If they don't become 0, it means that the solution, the optimization is infeasible, doesn't have any solution. Okay, this was one thing that I wanted to let you know. Also, the reasoning for tableau method, if you remember, we said let's briefly talk about it because we had huge pace at the end of the previous session. Let's briefly cover that again. So when we have an optimization problem like this, we convert it to this by slack variables. And here we have 7 variables, including the slack variables, but we have 3 equations, right? And this is the default constraint. I'm not talking about that. These are 3 equations in the constraints. So it means that in the tableau method, we will have 3 rows except the 0. So we'll have 3 rows, and it means that we'll have 3 basic variables. It means at the end, 3 of them will be non-zero, and 4 of them will be necessarily 0, right? So let's choose 3 out of 7. It means that we have 35 cases for having basic variables. Let's cover some of them. For example, here, let's take x1 to x4, which are the main variables. Let them be non-basic variables, and let the slack variables be the basic variables, and see what happens. Substitute this x1 to x4 equal to 0 in the optimization problem, and you'll see that. So here, if I set x1, x2, x3, x4 to 0, see the cost function will become 0, and these equations will be simplified to this, right? And therefore, S1 is 50, S2 is 42, and S3 is 250, and the cost is 0. Now let's go to another situation where we get x1, x4, s1, s2, set it to 0, and the basic variables, let them be x2, x3, and s3. Okay, now let's maximize this. So the cost becomes 6x2 because the rest will be 0, and the constraints will be simplified to this, right? And if you from this you can get x2, substitute this in the first constraint, you will get x3, and then put it here, substitute it here, you will get s3, and you will have this, and the cost will be 6x2 star, which is 84. So now compare this cost with the previous cost, and you will see that this cost, the second cost that we found, is better. Therefore, this solution is better than the previous solution. These are better basic variables than those 3 chosen basic variables previously. Now, let's come here. So a fundamental question here is that which variable should we increase, which maximizes the cost function the most, or which variables should we take as the basic variables, right? For example, in this cost function that we have, we want to maximize this cost function, right? So we can change x1, x2, or x4. Which one should we increase, which has the most effect on increasing C? Of course,
X4.
Yes. What? Which one?
X4.
X4, does X4 increase the cost function?
X2, sorry, X2.
No,
X2, exactly. Yes, exactly, X2. Because when you increase X4, the cost will
The
be
negative
reduced.
sign, yeah.
Yes, exactly. So let's increase X2 because it has 6. It is multiplied by 6. X1 is also multiplied by a positive number. However, 4 is less than 6. Therefore, X2 has the most effect. Now, when we bring the right-hand side of the cost to the left-hand side, as we do in the tableau method, where this means that the most negative number, which is multiplied by that variable, let's take that variable as the pivot column, right? That's why we take the most negative value in the 0. Why we want to find in the pivot column, we want to find the variable which maximizes or increases the cost the most, because we are maximizing, right? So this is what we are doing in that's why in tableau method, in the 0 for maximization problem, we find the most negative number, like what we have done here. Okay, what's the reasoning? So that was the reasoning behind pivot column. What's the reasoning behind mean test and pivot row? So let's see here. Okay, now consider these constraints, and this is the cost, right? So x2. Okay, assume that. Give me a second. In the first constraint, the worst case scenario is that x1 equals x3 and s1. They are all let them be 0, and the most we can increase is x2. So again, after choosing x2 as the pivot column, now let's go to these constraints one by one. Consider the first constraint, x2. We are considering x2 as the pivot column. In order to increase x2, what is the worst or best or worst case scenario? What is the extreme case scenario? Is that we set x1, x3, and s1 to 0. Why? Because they can't get negative, right? So the least amount for x1, x3, and s1 is 0. So let them be 0. So we have the most value for x2 in the first constraint, right? Is it clear? So assume I put s1 as 10 and x3 and x1 as 0. x2 will be 40, because 40 plus 10 becomes 50. 40 is less than 50. We want to assign the most value for x2, for the chosen x2 in the pivot column. So that's why we are setting the other ones to 0. Now in the next constraint, we are considering x2. Let x1, x4, and s2 be 0. Extreme case scenario. So the biggest value for x2 will become, so 3x2 will become 42. So x2 becomes 42 divided by 3. And now you see we have done this in the mean test exactly. Here, that's why we were dividing right hand side to this. And this is the multiplication factor of x2 in the first constraint. Also, we are dividing 42 by 3. And what is 3? 3 is a multiplication factor in the second constraint. Also, again, in the third constraint, the extreme case scenario is we don't have any x2, right? We don't have any x2. Extreme case scenario is that we set them to any number, but we don't have any x2. So setting x3 and x4 and s3 to any number doesn't have any impact on the x2. Therefore, you can consider 0 alpha equals 250. If you set x3, x4, s3 to 0, you will have also the 0 times x2. So x2 becomes infinite. So now let's take here, consider this x2, this and this. We have this, right? We have these 3, which we have done in the mean test as well. Now, what is the biggest increase of x2 that we can have? It will be the minimum among these, right? Because if you take infinite, these two constraints don't allow that. You can't increase x2 to infinite because of these two constraints. Now consider, for example, 50. If you take x2 as 50, what happens? This constraint doesn't allow that. It says that if I put x2 to 50, 3 times 50 becomes 150. And but this means that, and the right hand side is 42. It means that 2x1 plus x4 plus s2 will be negative. How is it possible? Because x1 and x4 and s2 are non-negative variables. Do you remember? We are talking about the standard linear programming optimization problem, right? That's why, we should take the minimum among them, because the minimum increase of x2 will restrict others to increase. That's why it's called mean test. We take a minimum among them. This is the minimum that we can increase x2 for increasing the cost function. Now This explains why we choose pivot row based on the mean test. Is the reasoning clear? That was why what is happening behind the scenes for the tableau method. That's why. Is it clear? And as you see in the simplex algorithm, we are moving from extreme point to extreme point, and from an extreme point to its neighbor extreme point, in order to increase, if we are talking about maximization, in order to increase the cost function the most. For example, if I'm at one of the extreme points and I have two other extreme points, three other extreme points, for example, one of the extreme points, which is neighbor to me, makes the cost function worse. It has less objective function, right, than me. Therefore, I don't move toward that because I want to increase the cost function. Now consider the two other extreme points. Let them have higher objective function value than me. Therefore, moving to either of them will improve the cost function. But you tell me, which one should I go to? Which one should I go to? Can someone answer? Assume I am in an extreme point and I have two other extreme points. The third extreme point, for example, it makes the cost worse. I don't go toward that. There are two other extreme points. If I move to either of them, they will improve the cost function. But which one do I move to? How can I decide which one is better? And if you answer me, please, I will appreciate that. Okay, let me explain this way. Assume at this point, my cost is 40. At one of the extreme points, my cost is 30. So it gets worse. I don't go from 40 to 30. I want to maximize that. In another extreme point, my cost is 42. In another extreme point, my cost is 48. Should I go to the extreme point with cost of 42, or should I go to the extreme point with cost 48? I think I don't have your voice. Are you answering me? Okay, the cost 48. We need to go to cost 48. Yes, someone in the chats has asked the direction with higher slope. Not necessarily with higher slope. We should go to the because we are not moving along the directions necessary. We want to move along a direction which increases the cost the most. As Ashwin has said, 48 is the correct answer, right? So, okay. Now let's go to the dual problem for minimization. Well, there is one, okay, what is dual problem? And dual problem will be introduced to you in KKT slides better. But here, just for the sake of understanding it, when we are minimizing a cost function, assume if, we can find a dual problem which maximizes another function g, right? And the solution of minimization of f, so the argmin of f will happen at the same argmax of g. So whenever we have argmin of f or argmax of g, they happen at the same time. So as you see, minimization of one of them is maximization of the other one. If we have a maximization problem, if f is this, we minimize a problem, we find a problem, a minimization problem, and that would be the dual problem for this maximization. Again, as you see here, there is a duality. So either you have a minimization, you convert it to a maximization problem, or you have a maximization, you convert it to a minimization problem. So one of them is a dual of the other one. And we will see how we can find dual problem for linear programming. Consider this minimization problem. So far we talked about maximization in linear programming. Now let's talk about minimization. So when we have a minimization problem, let's use dual problem for minimization in order to have a maximization problem, and then solve the maximization problem. And an example minimization problem is this, where the constraints are here, for example, greater than or equal to something. In the maximization, we usually had less than or equal to, right? But the objective variables are still non-negative. Consider this example again. Now we want to find a dual problem for this optimization problem. What should we do? Consider the first constraint here, right? I multiply it by some variable which is non-negative, some non-negative variable, and it will have y1 x1 plus 2y1 x2 greater than or equal to 40y1, right? And why doesn't it change this direction of the inequality? Because the y1 is non-negative. We also do the same for the second constraint, and we use y2, and we'll have these. So these two will have. Okay, now let's sum these together, sum the sides of these two together, and we'll have this. So if we sum the left-hand side, we'll get this. If we sum the right-hand side, we'll get this, right? And the inequality are both greater than or equal to. So we'll have this. On the other hand, this is the cost of the minimization problem, right? And we want this to be the best lower bound for this cost. As you recall, I said when we are minimizing some function, the dual problem tries to maximize some other function. And as you see, this other function is a lower bound, is always below this f function. So it's a lower bound. When it's above some function, it's upper bound. So f is upper bound of g here, g is lower bound of f. We want to find the best lower bound. So consider these two g. So for this f, let one of the g1 be this and g2 be this. Which one is a better lower bound for f? Can someone answer me? Which one is the closer lower bound to f?
G1.
G1, exactly. You know, in technical words, this is a tighter lower bound. This is a tighter. Thank you. Yeah, also someone said G1. So it's a tighter lower bound. We are closer to the function here. Therefore, we want to find the best lower bound, the tight lower bound in dual problem. That's why we are saying that let it be the lower bound for the actual cost function that we have in our minimization problem. Now consider these two. I'm repeating them here. I'm repeating those two inequalities here. Now let's consider these two together. So this is greater than this. Also, the same thing is repeating here. This is greater than this. Right? Therefore, from this we can decide this. It implies this. Why? Y1, what is the multiplication of x1 is y1 plus y2, and we have also the factor 12 for x1. Also, we have 2y1 plus y2. We have the multiplication factor 16, right? And this is greater than or equal to. It means that 12 is greater. In order to have this inequality, we should have 12 is greater than or equal to y1 plus y2 here. Also, 16 is greater than or equal to 2y1 plus y2. We have it here, right? Okay, and also this is a lower bound that we want to find for the cost function. This is the cost of minimization. We can call it f, and we can call it cost of g, the dual problem, right? So f is this, we are minimizing it, and the dual problem has a function g which is lower bound, and this inequality, these two inequalities show that this g is a lower bound for f. And therefore, we want to maximize it because, as we talked about it in dual problem, whenever we maximize the function g, it means that we are minimizing the function f. So we maximize the cost function of the dual problem, and the variables now are y1 and y2. So the variables changed. In the primal problem, this is called the primal problem, the minimization here, or f. In the primal problem, our objective variables were x1 and x2. But in the dual problem, we are calling it y1 and y2. We can call it anything, but we are calling it here y1 and y2. Now we are maximizing for this lower bound. We want to find the best lower bound, the tightest lower one. That's why we are maximizing it. And we also have these two constraints that we found. So we'll have this problem, maximizing this with these two constraints. And we also assume that these two variables are non-negative. Why? Because when we were recall here, when we were multiplying the sides of constraints by some variables, they should be non-negative in order not to change the direction of inequalities. Again, as you see, what is it? Did we have that? This is exactly linear programming maximization that we had in previous slides, right? So you can see that when we have some minimization in linear programming, we can simply find the dual problem for that, and it becomes a maximization problem, and then we can solve it using the tableau method that we already discussed. That's very simple. So this maximization problem is exactly what we had before. But and don't be confused with the names of the variables. So in mathematics, we have whenever we don't care about the name of the variable, we call it dummy variable. What does it mean? For example, an example, sigma I from 1 to n, I to 30, for example, I squared. What is it? It is 1 squared plus 2 squared until 30 squared. Does it matter if I change this to j equals 1 to 30? No. Does it matter if I say chair from 1 to 30? No. So j squared, chair squared. I don't care about the name of the variable here. That these variables are called dummy variables. Also here, we are solving some optimization problem which has some variables, and these variables can have any name. You can call the variables x1, x2, you can call them y1, y2, you can call them chair1, chair2, you can call them anything, right? That's why don't be confused with the name of the variables. These are your choices to choose a name of the variables. Clear so far? Right? Okay. Now let's solve this example. For example, the dual problem that we found. Let's solve it very quickly. We have the variables. We have the slack variables, so we converted them to the inequalities to equalities by a slack variable, and we formed a table, and we get the biggest negative number in the 0, -40. So this is a pivot column. We do the mean test, and we get the minimum among them, and this chooses the mean row, pivot row, and then we do the elementary row-wise calculations. So we'll have this table. Let's go to the next slide. Okay, I have then let's get the biggest negative number in the 0. It gives me the pivot column. Now let's do the mean test and take the mean among them. And so this gives me the mean, the pivot row. Now let's do the elementary row-wise calculations. I will have this table, and I will see that in the 0, all of them are non-negative. It's non-negative. All of them are non-negative. Great, so it's done. Optimization is done. And from here, we can say that y2 is a basic variable, which is 8, and y1 is a basic variable, which is 4, and the other ones are the these two slack variable, the slack variables here are the non-basic variables. Let's check whether our optimal cost is correct or not. So if we substitute these into the cost, we'll get 400, which is correct. And there is a theorem in linear programming that says that a strong duality holds for linear programming. So let's briefly explain what strong duality and weak duality are. We will go through them in the KKT slides, but here just we briefly mention that. What does it mean? Do you remember I said when we have a cost f, it's dual g, or vice versa. If we have here we are minimizing, here we are maximizing. We might have a maximization of f and minimization of g. Doesn't matter. There is a gap here, right? And as we discussed, the dual problem, consider this case for now for simplicity. The dual problem is always a lower bound for the primal problem. So if the primal problem is a minimization problem, and if the its dual becomes a maximization problem, then the dual function here will be always a lower bound. So we never will have such cases. Always G is below F, and vice versa. If our primal problem is a maximization problem, its dual becomes a minimization problem, and it means that the dual function is always an upper bound for the primal function. Doesn't matter. I'm saying that this never happens. This never happens, right? So we have either two cases, one of these two cases. Either we have some gap, positive gap, or the gap is 0. In both of these cases, G, the dual problem, is a lower bound for F, which is the primal problem. Is it clear so far? In both of these cases, right? This is called weak duality in optimization. And this is called a strong duality. This is the better case for us. Why? Why is it better, do you think? Assume I was going to solve an optimization problem, minimization of F, but it was hard. I converted that to a dual optimization problem, so I'm maximizing G. Assume I solve a maximization of G, and I get some variables, and I find the maximum of G. Now, if I'm in a weak duality, the maximum of G is here, right? If I'm in a strong duality, the maximum of G is here. In both cases, I have found the maximum of G. You please tell me, from the maximum of G, can I find the minimum of F in weak duality or strong duality?
Well, I guess in strong duality, it could potentially be equal, depending, I guess, like how strong it is.
When we say strong, it means that the gap is 0.
Well, then, yeah, it's equal.
Equal, exactly. So in a strong duality, the maximum value of G is equal to the minimum value of F, right? But in weak duality, there is a gap. So when we find the maximum of G, G plus something becomes the minimum of F. That's why a strong duality is better for us. If we have a strong duality, it means that we are relieved a bit, all right? And usually it's very hard to hold. Usually we have weak duality. But I think in practical examples, we might have a strong duality. So there is a condition that we will talk about, the Slater's condition. In practical examples, we can see that in engineering problems and these things, a strong duality can be assumed. Okay, so there is a theorem in optimization that we don't go over that. It has proof that's saying that a strong duality holds for linear programming. So when you have found the maximization of G, which is 400, what does it mean? What is the minimum? What is the minimum of F here? What was the problem? Let us go back to where we started from. This problem, right? Minimization of this. What is the minimization of this? Because of the strong duality, it's equivalent to maximization of this. With these constraints, for sure. With these constraints that we have. So the maximum of this was, we found it is 400. Therefore, the minimum of that function with those constraints is 400 as well, because we have a strong duality. So far clear? Okay, again, the problem that we have in hand is primal problem. The problem that we find for it, we convert that to, if it is minimization, we convert it to maximization. That problem is dual problem. So the primal, if the primal problem is a minimization, the dual is a maximization. If the primal problem is a maximization problem, the dual is a minimization. So I think you can consider them, in order to remember, you can consider them as two reversed bowls. One of them is going up, one of them is going down, and there is a gap, and not a non-zero gap between them. A non-negative gap. It might be zero gap, it might be a positive gap, but the gap can't be negative, so it can't be like this. It's either like this or this. This is the intuition behind the primal and dual problems. Now let's go to dual simplex algorithm. So don't confuse it with a dual problem. For in the previous slides, we said that we have an optimization problem. Let's find the dual optimization problem for that, and then you solve it using the simplex method that we already explained in the previous slides, right? And the previous session. However, we are now introducing dual simplex method. Again, the difference. We are now explaining dual simplex method. In the previous slides, we said, let's convert it to a dual problem and solve it using simplex, direct simplex method. Here, we are saying that, okay, what we had solved, we found the optimal cost function. And because of the strong duality, we said that the optimal value for the function in the dual problem equals the optimal value for the function in the primal problem. We have found that. However, what if the variables also, the optimal primal variables are important for us? What we solved in the previous slides didn't give us the optimal primal variables. It gave us optimal dual variables, right? So now, for finding this, we can say that let's use dual simplex method. And what is that? It says that, I will explain to you what it is, but how does it work for minimization? For minimization, we also can do a dual simplex method for maximization. We'll cover an example for it. But for minimization, it only works if all of the multiplication factors in the cost are non-negative, and also at least one of the inequality constraints is greater than or equal to 0. I will tell you why. Let me first explain the dual simplex method, and you will see the reason behind that. So here, this is a minimization problem. I don't want to convert it to a dual problem. I want to solve it directly using dual simplex method. So consider this. This is a pain in the neck, right? These were in the standard optimization problem for linear programming, because it is minimization. In a standard problem, we have less than or equal to. For maximization, we had greater than or equal to, right? Now, for this inequality, we have this. We can convert it to less than or equal to, which we desire in the standard linear programming problem for minimization, by multiplying by -1, right? We have greater than or equal to, let's convert it to less than or equal to. So if we do that, because of -1, the direction of the inequality is reversed, and these three become, by slack variables, become this, and here we also have this. So because if you remember, whenever we have less than or equal to, we use slack variables, because we can say that this is less than minus 150 because of this slack variable, assuming that the slack variables are positive. So we also should say S1, S2, S3, and S4 are less than or are greater than or equal to 0. And here we also have these variables. Right? Now we have this problem. Now let's solve it in this way. First, in the dual simplex method, as its name shows, we choose the pivot row. So in the simplex method, we chose the pivot column first and then the pivot row. In the dual simplex method, it's the other way around. We first choose the pivot row and then the pivot column. For the pivot row, we say that, look at this, it's something like you are transposing the table. In the right-hand side column, choose the most negative value. Remember, in the simplex method, which in the C row, we chose the most negative value. Now in the dual simplex method, in the right-hand side row, we are choosing the most negative value. So this gives us the pivot row. And now let's do the mean test in this way. Mean test, it changes a bit. Again, it seems that you are working with the transpose of the table. So you divide this by any non-zero values of the zero. Sorry. You divide. I apologize. Let me repeat this. You divide the non-zero values of 0, which are these, the non-zero values of 0, by the negative values of the pivot row. Right? The negative. And you take the absolute value. So minus 3 divided by minus 1, take the absolute value becomes 3. If minus 4 divided by minus 2, take the absolute value is 2. So now take the mean among them, which is 2. So this is the pivot column. Again, I think if you consider it as working with the transpose of the table, it will be obvious for you. It's similar to what we had, but transpose of the table. And so we chose the pivot column and pivot row. And now let's do the elementary row-wise calculations as before. So we have row 1, row 2, row 3, row 4. And we want this value to become 1 and the rest becomes 0. So I want these to become 0 and this becomes 1. Exactly. So again, exactly as before. Henceforth is like before. So here I should say R2 plus R4 time divided by 2. So it makes this row 0 and these things. Sorry, here for this row, for example, here I say R1 minus R2. For this second row, I say R2 plus R4 divided by 2. For the third row, I say R3 plus 2R4. And for the fourth row, I say minus R4 divided by 2. And for the C row, I can say what? You tell me. R5. So R5 plus 2R4. This gives me. And now, for termination condition is this. Again, like similar to the transpose of the matrix. All of the values in the right-hand side column should be non-negative. Previously, the termination condition was all of the values in the 0 should be non-negative. Now we are talking about right-hand side column. So now at the end, what is this? Again, like before, S1 here is a basic variable, 525. S2 star is a basic variable, 150. S3 is 700, and X2 star is 75, and C star is 300. You can also check that C star is correct. Now, as you see, we have found the optimal variables in the primal problem. Using the simplex method for dual problem, we couldn't find the optimum optimal objective variables. But now, using the dual simplex method, we can directly solve the minimization problem, and it gives us both the optimal objective function and optimal objective variables. So far clear? Is it clear so far? Any question?
Yeah, it's clear.
Okay, just one more thing that I want you to understand is that in both minimization and optimization problems, when we have less than or equal to, we can use slack variables, right? Do you remember when we had greater than or equal to, we were using either big M method by using two variables, or we can use this technique with multiplied by -1 and we'll have this. However, when we multiply it by -1, the right hand side becomes negative, and this forces us to use the dual method because we'll have some negative value in the right hand side column. If you remember, if you go back to the previous slides, in the right hand side we didn't have a negative value. And it's obvious why, because whenever the variables are non-negative, their summation are usually non-negative. That's why usually in the right hand side you see positive numbers in linear programming. However, when such cases happen and we are multiplying the size by -1, we are making one or several of the variables in the right hand side, the numbers in the right hand side column negative, and this forces us to use the dual simplex method. Another thing that I wanted to let you know that I think it's very interesting before I go to that next slide. I want you to understand the reasoning behind every step. So here in big M method, this is a great technique in optimization. In big M method, let me bring it because this is important to note. Why? Do you remember we had this? Let's consider this again. x1 plus 2x2 is greater than or equal to 150. So we have a greater than or equal to, we can't use a slack variable. Why? Because we said whenever, if we say, assume you use a slack variable, S. What does it mean? It means that because these are non-negative, and also this is greater than or equal to, it means that S is negative. But S can't be negative. In the standard problem, all S will be one of the objective variables, right? All of the objective variables should be non-negative. So this doesn't work for us. We said, what was our technique or trick? What was our trick? We said, let's replace S with two variables, saying that one of them, let it be additional variable. Let's call it additional variable. The other one, let it be excess variable. Now, this can be correct because both of these A and E can be non-negative, but A minus E might be negative. So whenever you have some variable here, like E, that it needs to be negative, but at the same time it needs to be positive, you can say, okay, I replace this variable with one variable and minus another variable. Let those variables be non-negative, but based on their values, the difference of their values, A minus E might be negative. And this also works for when you have an optimization problem. You might be wondering, so far whatever we said, that in the linear programming, we are assuming that the variables are non-negative, right? There is a valid question that what if the optimization variable is non-negative, is negative or non-positive, right? What if you have an optimization problem where x1 might be negative? In those cases, you can replace x1, assume you have some x1 less than or equal to 0 in the constraints. You can say, I will replace x1 with x1 plus x1 minus, so whatever name you want to choose, doesn't matter, k minus z. I replace x1 with k minus z, or k1 minus z1. I assume k1 is greater than or equal to, z1 is greater than or equal to, but the k1 minus z1 might be negative. So you see the technique. Whenever you have some variable, you it needs to be negative. However, at the same time, it needs to be positive. Why? Because in a standard problem, you have to have your optimization variables non-negative. Then you can replace it. It's a trick. You can replace it with a positive, non-negative number minus another non-negative number, but based on their difference of values, that can be negative. So this is a good technique. Clear so far? Yes?
Yes.
Okay, that was the trick used in Big M method as well. Okay, let me go to that slide that we were on. Oh, okay, we were here. So we said that the dual simplex, we use that dual simplex method. We use that for solving minimization problem. We can also solve it for maximization problem when to deal with the greater than or equal to constraints. Do you remember in previous slides we said when in maximization problem we assume that all of the inequality constraints are less than or equal to. If we have greater than or equal to or equality constraints, in other words, if we have mixed constraints, we use Big M method. However, there is another way to deal with greater than or equal to constraints in maximization problem, and that's using dual simplex method for maximization. We are going to cover it here. Okay, what is it? So again, the same thing that we had in several slides before. So assume that here, these are less than or equal to, so we can simply use the slack variables for them. However, we have a greater than or equal to inequality here. So this is a pain in the neck, right? What should we do? We can convert it to regular less than or equal to constraint. How? By multiplying it by -1. So we'll have this. However, another pain in the neck appears, and that's -1 in the right-hand side. And we should deal with it with dual simplex method. So this can be simply converted to this by slack variables because it's less than or equal to. Now, this problem is converted to this. So these three were simply converted to this by slack variables, but this needed a multiplication by -1. And then having a slack variables, and now all of the variables, including the slack variables, are non-negative. So this is a standard optimization problem. Now let's form the table for it. So this is a table. However, we have a -1, a negative number in the right-hand side column. Therefore, it forces us to use the dual simplex method. In order to do that, we said that we choose this pivot row as we talked about it before. So this because it's negative, so we choose this, and then we do the mean test. So for mean test, we say 5, absolute value of 5 divided by -1 is 5, but the rest are 0, so we ignore them. 10 divided by 0, we ignore them. 10 divided by 0, we ignore them. We also ignore these because these are we said in the mean test we choose the non-zero. Let me show you for recalling. We said for mean test in here in the dual simplex method, divide the non-zero values of the 0 by the negative values of the pivot row. Okay. So this gives us only this column. This will be a pivot column. Let's do we do the elementary row-wise calculations in order to make this 1 and the rest, these and these, 0. We have done it here, and then we solve it and we'll see, oh, here now in the right-hand side column, all of them become non-negative. So we can see that S1 star is 26 and so on. And we can also check that C star is correct. So as you saw, we have two ways to deal with a greater than or equal to constraints in maximization problem in linear programming. Either we use Big M method or we use dual simplex method. Okay. This lecture was inspired by the lectures of Professor Shakufe Mirzai. You can on linear programming, you can see her lectures on YouTube. I have put the link here. I'll also put it in the description of the YouTube channel. And yes, I think her slides are her lectures are very good for linear programming. And this is the reference for the first simplex method which was proposed in 1983. Any question before we move to integer linear programming? No? Okay. So let's do okay, someone said something. Not right now. Okay. So integer linear programming now, we are done with the linear programming. Let's go to integer linear programming. Do you remember linear programming? We had it here. So integer linear programming is the same, but it has an additional constraint. It says that the optimization variables are integers, either all of them or some of them. If all of them are integers, if some of them are integers and some of them might be float or not non-integers, real, then we'll have mixed integer programming. Okay. Usually, so this is integer linear programming. Usually when we say in the literature, we say integer programming. Integer, as we had talked about it before, programming means optimization. Integer programming means integer optimization. It means that any optimization problem whose variables should be integer, right? Other words, its objective variables are discrete. It's not continuous. It can be, for example, 0, 1, 2, 3, or -1, -2. So it can't be a value between 0 and 1 or something like that. It's not continuous. It's discrete. Its domain is discrete. And so integer programming refers to any optimization problem whose variables are integer. But however, usually when in the literature they call integer linear programming, they refer it to integer programming sometimes. So whenever you hear integer programming, they might be meaning integer linear programming. It means that the linear programming whose optimization variables should be integer. An example. Do you remember we had some practical examples for linear programming? This is the same practical example, but I have changed the amount to number. So in that linear programming, we said, okay, let's assume that we have a company producing 2 products, and let x1 and x2 be the amount at that time. So we said let x1 and x2 be the amount of the first and second products to be produced, and that amount can be any scale, like such as kilograms, grams, centimeters, or meters, and these are continuous because the length is continuous, the weight is continuous, and this is, however, in your optimization problem, it might be the number of products. So 1 candy, 2 candies, 3 candies, something like that. Then the variables are non-negative again, but they are integers. So, and the rest of the problem is the same. So you have these, but the variables are integers. Okay, an example is here. Assume that we are maximizing this problem, and the cost is here. These are the constraints. This is the default constraint. This is another default constraint for integer linear programming, right? But however, you might have only x1 is integer, or only x2 only integer. Then in those cases, we'll have mixed integer programming. However, when both of them are integer, it's a complete integer programming. And if you remember, so these are, we can draw x1 plus x2 less than 5 is this constraint, and 4x1 plus 7x2 is less than or equal to 28, so it will be this constraint, right? and x1 is and x2 are greater than or equal to 0. So they will be these constraints. And we know that x1 and x2 are integer. Before that, up to this point, our optimization problem was a linear programming problem, which is this, right? However, here, when we say it's integer, it means that x1 and x2 can be only integers. Therefore, we are only on one of these points. Because here, for example, x1 is 1, x2 is 1. Here, x1 is 2, x2 is 1. So, and we can't go outside of these constraints. So we are only here as we drew here. However, only integer values of x1 and x2 within these feasible set. So the feasible set will be only on these points that I'm drawing. Only on these points. I can't be here. I can't be here. I should be only on these points. So far clear? Also, these points are in the feasible set because they might be 0, 2. Right?
Yeah, it's clear.
Okay, great. Now, two very important questions for you to completely understand integer linear programming. The first question, and I'm happy to hear your answers. First, is integer optimization? Forget about linear programming and integer linear programming. So we have either continuous optimization or discrete optimization. And one case of discrete optimization is integer optimization. Discrete optimization is more general. For example, it can be the feasible set is discrete, but it's not necessarily integer set, right? It can be, for example, 1, 2.5, 3, 3.5, 4, 4.5, something like that. It's still discrete, but it's not integer anymore. Integer optimization is a special case of discrete optimization. Let's talk about continuous optimization versus discrete optimization or integer optimization, doesn't matter. You please tell me which one is harder. Is continuous optimization harder or in discrete optimization?
Discrete.
Yes, and can you tell me why?
Yeah, continuous, like we can just look at it and like you can just like it's a curve, right? Like it's sorry,
Yeah.
sorry.
Exactly. You're right. So we can move toward our solution with any step that we want, right? And hoping we reach that. So, and we are also smooth. So as you said, it's curvy. So we move, and the cost or the feasible set might not be smooth, but still we can move in the feasible set easily. However, in the integer programming, we need to jump, right? For example, here, my feasible set is like this. I jump either from here to here, here to here to here. I can't move with a fractional step, something like that. Is that clear? Yes?
Yes, but why couldn't we solve the problem like it's continuous? So like an example would be in the image you have, it's roughly like 1, 2, 3, 3. So let's say you get the answer like 3.2, 3.1, like for X and Y.
Okay.
Like couldn't you round down and then just get the answer 3? Like why couldn't we do that?
We can do that. We can do that. What you're saying is that basically let's reduce or relax. We can use any of these words for it. Let's relax or reduce our discrete optimization problem to a continuous optimization problem, solve the continuous optimization problem, and retrieve the solution of the discrete optimization problem from the solution of the continuous optimization problem. This is basically what you're seeing, right?
Yeah.
So this is exactly what we are going to do for solving integer linear programming. So we relax integer linear programming to linear programming, solve it, and then we retrieve the solution of the integer linear programming from the linear program. So this is exactly a good idea that came to your mind. And this is, yes, how one of the ways to deal with discrete optimization. It's not the only way. There are other ways too, but one of the easiest ways is that let's relax it. Let's relax it. So relaxation in mathematics is very well used. So people use it very much. However, your relaxation shouldn't, in any optimization or any mathematical problem you have or engineering problem, you can relax, but you should be careful that your relaxation shouldn't falsify some of the constraints of your system, right? So sometimes the relaxation completely changes the problem in a way that the solution of the relaxation is never related to the solution of before relaxation. So you should be careful how to relax your problem. However, as you said, assume that if we relax it in a way that it doesn't drastically change the problem, then we can retrieve the solution from the continuous solution. Yes, exactly. That's correct. So the second question is that, is the optimum value of the objective function before that, according to the first question, therefore integer linear programming is much harder than linear programming. So in general, discrete optimization is much harder than continuous optimization. Now let's go to the second question. Now let's only focus on linear programming and integer linear programming. I'm not now generally talking about discrete optimization versus continuous optimization in the second question. Specifically for integer linear programming, is the optimum value of objective function in the integer linear programming better or worse than the value in the linear programming? Optimum value. So I mean C star. The C star in integer linear programming versus the C star in linear programming. Which one is better? So assume I have a maximization linear programming. I have another maximization integer linear programming. Both optimization problems are the same except one constraint. In the integer linear programming, the optimization variables should be integer. So except that, they are completely the same, the constraints and the objective variable. The C star, which one will have the higher C star? Can you tell me? Just say your guess.
Like, so you're asking which value is better or worse, but wouldn't that depend on wouldn't that depend on the question? Like if you're asking, some questions would require whole numbers. Like if you're getting the maximum of people, you can't have like, say 4.2 people. So then you'd have to solve it using an integer, right? To get a whole number.
Yes,
So
but
it depends on the question.
Assume that the problem can be either continuous or discrete. I'm saying that consider these two. I understand that some optimization problems are only discrete optimization problems, but I'm not talking about that. I'm saying that assume I have two optimization problems exactly like this. I'm copying this here. Everything except the last constraint. These two. So problem 1, problem 2. Exactly the same, except the last constraint saying that x1 and x2 are integer. So we are maximizing this cost, the same cost, with the same constraints. This gives me C1 star. This gives me C2 star. What is the relation between C1 star and C2 star? We have either C1 star greater than or equal to C2 star or C1 star less than or equal to C2 star. Which one is correct? Even before solving it. In other words, this is the feasibility set for this problem, and this is the the other way around. This is the feasibility set for this problem, and this is the feasibility set for this problem, right? Both have similar feasibility sets, but here we are only allowed to be integer. can you tell me if which one will have higher optimal cost?
Is it C1 is less than C2?
Yes, and can you tell me? You're right. So C1 star, which is in the integer linear programming, is less than or equal to C2 star, which is in linear programming. Can you tell me why?
I don't like I can just visualize it in my mind that like C1 can never be greater than C2. Like just by looking at the graph, I can tell that, but I can't like mathematically elaborate.
Yeah, I understand.
Apologize.
You're right. You're right. Your intuition is correct. But if we want to see why more theoretically, is that do you remember in the last session we discussed that in the linear programming, the solution is only in one of the extreme points, right? So here either this or this or this or this is a
Yeah,
solution.
it has to be a vertex.
Yes, exactly. Vertex of the feasibility set, right? Because the feasibility set is a simplex or a polyhedron. However, in the integer linear programming, the feasibility set is discrete, and we are now in integer linear programming. It might not necessarily be a vertex. Why? Because it might be close to a vertex. So, for example, your feasibility set is like this, and your integers are like this. Assume your integers are like this. The vertices are not on the integers, and assume your cost is improving in this way. So if it was linear programming, the solution would be this vertex. However, as it is integer linear programming, the solution would be this integer point, because this is the closest to this. Even visually, you can see that this has less cost than this. Or you can say that if the extreme point of the solution is an integer, then C1 star would be equal to C2 star. However, if the extreme point is not an integer, then you have to choose the closest integer to that extreme point. Then it means that its cost is less than or equal to the cost in the linear programming in the extreme point. Is it clear?
Yep.
Yeah. So it means that the solution of the integer linear programming is always upper bounded by the solution of the linear programming. Now let's move on and say how we should solve this. Again, as one of you said, so we have this problem, we want to solve it. Let's relax it. Let's relax it to a linear programming problem in this way. We have relaxed it, so we have dropped these constraints, right? We have dropped it. This is a linear programming problem. If we solve it, we can either solve it because we have two variables, we can solve it visually, or we can use simplex method, tableau method, whatever we have, and we will come up with this. For example, visually, we can intersect these two lines and calculate the cost at these four extreme points and see which extreme point has the higher cost, right? And so this is the solution. And as you see, x1 star and x2 star are not integer. We called it subproblem 1. Subproblem 1. So we can, as I said, we can solve subproblem 1, which was a linear programming problem, by a tableau method that we discussed in the previous lecture. So we can have this, form this, and we have mean test, pivot row, pivot column. I'm solving this problem, right? And then at the end, I will have these, all of these are all are non-negative. So I have these two are basic variables, and this is C star. I can also check that this is correct. So I solved it. Now the trick is this. So I have this subproblem, which was a linear programming, so which was a relaxation of my problem to a linear programming, and I found these solutions. However, these two, x1 star and x2 star, are floats, are non-integers, are real numbers, right? Let's go to two cases where x2 is less than or equal to 2, or x2 is greater than or equal to 3. Why? Because x2 here, x2 star, is 2.67. First off, why do I choose x2, not x1? I can choose either of them, but I want to find the solution sooner. Therefore, I choose x2, which has the higher float number. So its float number is 67. Its float number is 33, right? 67 has a higher float number. I want to tackle that first. Tackle the largest float number first. Let that become integer, and then we can work on the other variables. So at each point, we divided the problem into two problems, sub-problems, where we are tackling the largest float number. So here, x2 star has the largest float number, and then 2.67 is between 2 and 3 with integers. So 2 and 3 are the integers around 2.67. Therefore, once I assume x2 is less than or equal to 2, or x2 is greater than or equal to 3. As you see, we are making a tree. We are making a tree. Or we are branching, right? We are branching this problem into two sub-problems. And also we are bounding the variable, which was a float variable, into bounding it by integers. That's why this method is called branch and bound. So you're branching and bounding as a tree. You will have a tree structure. Now, let's call it sub-problem 2. So we had this. Do you remember? Except this, which we just added, this cost and these three constraints were in sub-problem 1, right? Which was a relaxation of our main problem. So our main problem was relaxed to sub-problem 1, which are these. Now, in this branch, we are adding this constraint. This is another linear programming problem. It's not integer, it's linear programming. And we can solve it either visually or by tableau method. Here, visually, as you can see, so we had these two constraints in the sub-problem 1. Now in sub-problem 2, we are adding a third constraint, which is this another constraint, which says x2 is less than or equal to 2. So the feasibility set from here is reduced to this only. Now among these, so one of these extreme points is the solution. We can calculate the cost. So we can calculate the intersection of these lines and find these extreme points. And then we can calculate the cost at these extreme points and see which one has the highest cost. So that would be the solution to that sub-problem. So that sub-problem gives us this. Interestingly, that the solution of this linear programming problem is integer. Why? Because the more we go in this tree, the more restrictions we have on the feasibility set. Eventually, our solution has to become integer. In other words, when we restrict our feasibility set in this tree structure, at some point in this structure, the feasibility set becomes so small that one of its optimal extreme point falls exactly on some integer. This has happened here. In sub-problem 2, the cost is increasing this way, and accidentally or interestingly, the extreme point is on one of the integers for both x1 and x2. Therefore, we can say, okay, great, that's great. So we stop here for sub-problem 2. We don't continue sub-problem 2 we don't branch it into two sub-problems because its solutions, both of them, are integer, right? We can also solve the sub-problem 2 by, as you say, by tableau method rather than the visualization. Now let's go to sub-problem 3. Here we have subproblem 3, which was here, which was the cost. These are the two constraints, and this was a default constraint. Now we are adding this. So this, and this were in subproblem 1. We are adding this here. Again, this is a linear programming problem. We learned how to solve it in the previous lectures. For example, here you can use either, it's a maximization. With this, we can use either big M method or dual simplex method, right? Or as we have only two variables here, we can use it, solve it using visualization. Now we had these two constraints. Another constraint is added, which is this: x2 is greater than or equal to 3. This was the feasibility set. Now it has been reduced to only here. We can find the extreme points and calculate the cost, and we'll get the exact value. And I think for visualization, it would be easier for you if you use ruler and exact distances of the units. Otherwise, you might be confused at some points, especially when the feasibility set becomes very small. You might be confused. So ruler might help. So C star, x1 star, and x2 star are found. How x2 star has become integer, interestingly, right? However, x1 star is not integer yet. Therefore, we have to continue subproblem 3. However, which one should we choose, x1 star or x2 star? We should choose x1 star because x1 star has 75 as float. However, x2 star has 0 as float. Which one is larger? We want to tackle the larger float number, the float value, which is this. So we divide subproblem 3, branch it by on x1, and x1 is 175. It's between 1 and 2. Therefore, one problem will have x1 is less than 1, and another one is x1 is greater than or equal to 2. Here, before going to subproblem 4, which I was discussing, we can form the table and solve it. I haven't continued, but you can solve it for yourself. Here in subproblem 4, as I said, this is the subproblem 3 that we had in the previous slides. Now we say that as we talked about it, so this 175 is less than, it's between 1 and 2. Therefore, we have these two constraints. So these three and this default one, they were all in subproblem 3. This is added newly. x1 is less than or equal to 1, right? So as you see, in each branch, I'm adding to the constraints. So we had these three constraints in subproblem 3. I'm adding this constraint as a new constraint. Therefore, the feasibility set is reduced from this to only this. Now let me solve it either by visualization. We can find the extreme points here by intersecting these lines. You can find the extreme points and calculate the cost function, cost value in each of them, as we are maximizing, find the highest cost. Or you can use a tableau method, simplex method, and find this, right? C star. Interestingly, x1 star is integer now. However, x2 star now is float. So in subproblem 3, x2 star was integer, x1 star was float. We branched over x1. Now in subproblem 4, x1 has become integer, x2 has become float again. So we have to continue on x2 now, because the float of this is 0. The float of this is 42, which is a larger float. Again, this is the subproblem 4, right? And we can write the tableau method for this, or you can solve it using visualization. And as you see, the more the deep we go in the branches, the more constraints we have, the harder the tableau method would become. And don't worry about that. In the assignments, as well as the exam, I will give you, in the integer linear programming, I will only give you the problems with 2 variables. Therefore, you can solve every step of the this branch and bound method using just visualization. So don't need to worry of how you're gonna solve the tableau method for a lot of number of constraints in the branch and bound method. You can solve that using visualization for integer linear programming. Now, so do you remember in subproblem 3 we had this? We also showed how to solve the subproblem 4. Now subproblem 5. What is subproblem 5? Is this? So we have this. We also have this, and this default from subproblem 3. This is added here, and now let's draw the constraints to figure out what is what. So again, here, if you use ruler, that would be better. So you can see if there is a feasibility, any intersection between the constraints or not. Here, for example, so this is this constraint is this. We had this from the subproblem 3, from the parent subproblem. So what happened? Yeah, we also have this from the parent subproblem. We have this default because we are in the first orthant. Now we are at, we also, sorry, this shouldn't be in this figure. I will correct that in this slide. So we also are adding this. And as you see, there is no intersection of feasibility set. Do you remember in the first session, I said you should be careful that your constraints are not contradicting each other, because in that way, your feasibility set will be empty and your optimization problem will not have any solution. This has occurred here. At some point in the branch and bound method, some of the subproblems might face this issue. They might not have any feasibility set. In this case, there will say no feasible solution for that. No answer. So we can't continue this branch anymore. However, we can continue this because here we have x2 star with 3.42 and it's still a float number. Okay, here we are here. Now, among x1 and x2, which one has the largest float number? X2. Therefore, the branch split over x2, and 3.42 is between 3 and 4. Okay, so once we say x2 is less than 3, or once we bound it by 4, x2 is greater than or equal to 4. So let's see which one is it. Subproblem 6 will become this. So we have this, we have these, and these defaults from subproblem 4, and this is added here. If we put all of these constraints in the visualization that we have here, we will see that. So what we consider these two constraints, they are not contradicting. The intersection of these two means that x2 is equals 3, because x2 should be greater than or equal to 3. We had it from previous subproblems. Now we are adding another constraint which says x2 is less than or equal to 3. They are not contradicting. If they were contradicting, the feasibility set would be empty and we wouldn't have any feasible solution. However, here intersection is x2 equals 3. So it means here and here, it means that we are on this line. And so the feasibility set is, let me see. So x1 is greater than or equal to 2. Great. Yeah. So if you solve it, I think there might be some typo here, but I will look at it. But eventually you will see that the solution is this. Okay. But the feasibility set here will be only a line because x2 equals 3. Now, let's go to subproblem 7. where we have this and this from subproblem 4. And this is added from here. If we put all of these constraints together, and in the feasibility set, we find the extreme points and we solve that, you will see, or we use the tableau method, we'll get this. Interestingly, in both subproblem 6 and 7, both of the solutions are integer. As I said, the more you go in the tree, the more restrictions you have on the feasibility set, the smaller the feasibility set becomes. Therefore, at some points, the extreme points fall, the optimal extreme point falls on an integer solution, and you should stop there for that branch. We stop here. We also stop here. In the other branches, we also stopped. So the branch and bound method is over. Let's put all of them together. Let's put all of them together. We have this. So we started with subproblem 1. We split it over x2. Here we stopped because these are integers. Here we continued because this is still float. We branched over x1 because it's float. And then we have subproblem 4, 5. We saw that subproblem 5 is infeasible. In here we solved it. This is still a float. We have to continue over this. So x2. And we have this. So, but however, note that if we have multiple objective variables, such as 3, x1, x2, x3, we still have a binary tree, because at each subproblem is branched into 2 subproblems where we are branching over the objective variable with largest float number, right? So it's not binary because we have 2 variables. We might have 100 variables, but it's still we have a binary tree. Okay, now so we should look at the children of this tree. So we shouldn't look at these. We shouldn't look at this because its solutions are float. These are not integer. We shouldn't look at this. Its solutions are float. We shouldn't look at this because it's infeasible. We shouldn't look at this because its solutions are float. We should only look at this. These are the children, right? The feasible children. So this is also a child. However, it's not a feasible child. So look at the feasible children, which have integer solutions. Now we should choose among these. Which one is the correct answer? So you can see we are maximizing the, we have a maximization problem, right? Which one has the highest cost? This. So this is 27, this is 23, this is 24. Of course, this is the solution, right? So this is the solution, and this is t star is 27, x1 star is 3, and x2 star is 2. The final solution is the maximum objective, has a maximum objective function value among the feasible children. So again, this lecture was inspired by lectures of Professor Shukufeh Mirzai, and you can see her lectures too. They are very interesting. So by the way, this is a reference for mixed integer linear programming, where we have some of them integer, some of the objective variables integer, and some of them float. Before I ask you for any questions, just let me tell you one more thing. So what we discussed here was integer linear programming, where the objective variables are integers, right? We assume that all of them are integers. However, assume that in this problem, let us discuss it. For example, you have some problem like this. How should we handle this? Assume, yeah. So we were solving this subject to x1 is less than 5, 4x1 plus 7x2 is less than 28, x1 and x2 are greater than or equal to 0. What we solved so far was x1 and x2 belong to Z, and Z means integers, right? So we solve this. However, assume another example is that x1 is in Z, but not x2. I'm not sure, but maybe I bring this in your exam, so I think it would be easier and easier problem. But I'm not sure. I should think about it. But I think it's you know how to solve it, right? So it means that x1 is integer, x2 is not integer, not necessarily integer. It's generally float. So what does it mean? That it means that when you are branching, you should only care about whether x1 has a float value or not. If x1 has a float value, then branch on over x1. If x2 has a float value, it's valid. That's fine. So some of your valid children might have x1 integers and x2 float. Some of them might have x1 integer, x2 also integer. Among these children, you will choose the highest cost. And you should please note that if x2 has float and x1 is integer, you shouldn't continue branching, right? Because that's valid. So this is mixed integer linear programming, because some of the objective variables are integer and some of them are float. Is it clear so far? Any question?
Yeah, it's clear.
Clear? Okay. So if you don't have any question, let's have a break. And let's come back at 9:05. Is that fine?
Yep.
Okay, great. So we'll see you back in 9:05. Thank you. If you agree, we continue. Do you agree? Is everyone okay with with continuing the session?
Yeah.
Yeah, great. Okay, sure. Great. Now let me share screen. Okay, now so far we have talked about linear programming, so preliminaries linear programming and integer linear programming. Now we are gonna talk about sensitivity analysis in linear programming, sensitivity analysis. And afterwards, we'll go to KKT conditions, and afterwards to first order methods and second order methods, and so on. Okay, what is sensitivity analysis? It means that we want to see how sensitive our linear programming problem is to some change in the problem. So assume we have solved the linear programming problem, and now we change something, we make some change in the optimization problem, and see how sensitive is the solution, is the optimal solution to that change. Does it change or not? And if yes, how much? And we should see this. And this concept is also very useful for people in industrial engineering, especially, and management and these areas. Because, for example, the manager, we will see some examples. The manager might say, I want to increase the profit or the product of the first product by this amount. Do you recommend this or not? Because industrial engineers should recommend, make some recommendations to the manager of the company or these things. So they are usually consultants. So that's why this is an important topic for them. They usually have a lot of linear programming problems in their work, and they can just see the sensitivity analysis in their problems to know what to say to the and what to report to the manager of the company. Okay, so first off, consider this optimization problem, linear optimization problem, and assume we have n variables, x1 to xn, m constraints. These are m constraints, right? As you see, m constraints, and assume we also excluding these default constraints. These are also the default constraints in the standard linear programming problem, right? So we can write this and assume I write the multiplication factors in the cost function by C1 to Cn. So Ci is the multiplication factor of xi. Just give me a second. Yes, sorry about that. Okay, so Ci is the multiplication factor for xi, and now assume that Aij is the multiplication factor of xj in ith constraint, right? So Cj, xj, we have Cj is the multiplication factor of xj in the cost, and Aij is the multiplication factor in the constraints. And when we say A, for example, 3, 2, means that it is the multiplication factor of x2 in the third constraint, right? Also, let the right-hand side of the constraints be denoted by B. Let me bring this up. Okay, so let Bi be the right-hand side of ith constraint. And why have I written it by equality? Because I assume that some of these x's might be slack variables, right? So I have converted the problem in a way that we only have equality constraints. Now, for example, this problem. By the way, do you see this on top of the screen? Oh yeah, now I think you can see the full screen. Okay. So this problem is converted to this problem by slack variables, right? And I have this. So now while we had 3 objective variables, I have 6 objective variables right now. So in this converted optimization problem, assume that we have already solved a linear programming problem by tableau method, or by visualization, whatever method, or by simplex method that we know. And assume at the end, we found out that the basic variables are these. These are the non-zero. These will have non-zero optimal values, and these are necessarily 0, right? These are non-basic variables. Assume. So I can put the basic variables together as a vector with any order that I choose. But whatever order you choose, you should stick to that until the end. So now assume I put S1 first, X3, and then X1, because these are the basic variables, right? Assume I have solved it, and at the end, these are the basic variables in the optimal solution, and these are the non-basic variables. I put the non-basic variables together with some order, but I will stick to that order until the end. I will name this XB for basic variables, and this means define, right? And I will also name it XN. And these are the column vectors, right? This is transpose for becoming column vector. Now, let's put the coefficients of the basic variables in the objective function. Do you remember? These were C, right? Ci or Cj. So this was C1, C2, C3, right? Now I put them together, however, with the same order as this. So here I put C for S1. There is no S1 in this objective function. Therefore, I put 0 for that. This is the multiplication factor for x3 in the objective function, 20. The multiplication factor for x1 in the objective function, which is 60. Also, I call it CB because these are for basic variables. Also, I can have Cn with the same order as this. So we have 30 for x2. We also have 0 for s2 here, 0 for s3 here, right? And I'm defining some vectors and matrices for you, and you will see how we are going to use them. So again, now ax1. So I have these. I have a. Do you remember a? A is the multiplication factors in the constraints. Now I put them as vectors. So these are the multiplication factors for x1 in the 3 constraints. So because we have 3 constraints here, right? Excluding the default constraints. So we have 8x1, 4 in x1 in the second, and 2 in the third constraint, right? If I choose this order of constraints, because these are related to constraints, right? I can choose any order of constraints, but whatever order I choose here, I should stick to that order for all of these. So here also for x2, I put 6, 2, 1.5. For ax3, I put 1, 1.5, and half. For s1, I put 1, 0, 0. For s2, I put 0, 1, 0. For s3, I put 0, 0, and 1. Right? Now, so these are a's. Now the b, let this vector, the right-hand side of the constraints, be with this. Again, with the same order that you chose for a vectors. So 48, 20, and 80. I put them here. I call this b. And b is the right-hand side of the constraints. Okay. So I'm repeating those here for you to, because I'm gonna use them in these 2 newly defined matrices, B and N. B is M by M if M here is 3, right? Because we have 3 constraints excluding the default constraints. So B is a 3 by 3 matrix here. And it is, so we put these as columns of A, as columns of B. So AS1, so it means that what are the basic variables? The basic variables are S1, X3, and X1. And why do I choose this order? Because I already chose this order here. Do you remember in the previous slide? I also have repeated here. So I should stick to this order until the end, as I said. So I put AS1 here. This is a vector. This is a vector. This is AS1. Where is it? It's here. It's a column vector. So 1, 0, 0. I put AX3 here. What is it? AX3. It's here. It's a column vector. I put it here. AX1. So it's with AX1 here, here. Where is it? It's here. I put it here. So what is B actually? This B is in having all of the coefficient multiplication factors of the basic variables in the constraints. So these are the multiplication factors of basic variables in the constraints, right? The same we have for non-basic variables. We call it n. So with the same order that we chose before for xn, we put ax2. Where is it? It's here, here. AS2, sorry, with this, where is it? It's here. I put it here. And AS3, where is it? It's here. So I put it here. So, and what is the dimensionality of n? Is m by n minus m. What is n here? N is also 3. So that's why n becomes 3 by 3, 6. Sorry, I think there is a mistake here. Let me fix it. N must be n. A's are m dimensional vectors, so this is correct. And what is this? So yes, exactly, that's correct. That's correct, because here n is 6. I was mistaken. N is 6 because of these slack variables, right? So 6 minus 3 is 3. And why is it? Why do we have this? So I think the first dimensionality is obvious because the A vectors are m-dimensional because we have m constraints. And why are these? Because we have m basic variables. The number of basic variables equals the number of constraints excluding the default constraints. And we have n minus m non-basic variables. The rest of the variables are non-basic. So far clear? Yes? Okay. Now, interestingly, again, if we solve the linear programming problem by tableau method, at the end, we will have this format. And what is this? If assume you put all of the non-basic variables here, by the way, note that you might, at the end, when you solve the linear programming problem by tableau method, you might have some columns which are non-basic variables at the ends, and some of them are basic variables, and they might be next to each other. For example, you might have non-basic, basic, non-basic, basic, basic, non-basic, something like that. If you put all of these basic, you can rearrange the columns, right? If you put all of them together, so become here, basic variables, and rearrange the columns in a way that you put non-basic variables together, and you always have basic variables here, right? You remember, you have basic variables here, because in every pivot row pivot column, when you choose, you replaced the name of the pivot row by the name of the pivot column. That's why at the end you will have basic variables here. Now, if you do that, you will see that you will have this format. You will have B inverse B here. I'm not gonna prove this for you, but some intuition behind it, why it's gonna happen like this. So these, so let me see here. So you have this is B, right? Let me bring it. And what was B, capital B? So this is a small b, and capital B are these coefficients for the basic variables. Therefore, in order to have the basic variables, so you have kind of B x equals B, right? For basic variables, I'm talking. In order to have x, the basic variables, you need to have B inverse B. That's why. So this is the intuition behind this. Kind of. And also some other intuitions, let me think. For example, what is what is the relation between xp and xn? It's B inverse n. You can see it as n are the coefficients or multiplication factors for the non-basic variables, and capital B is the multiplication factors for the basic variables. So you can relate these together by B inverse B. Kind of B inverse cancels B, and n brings that to the non-basic variables, something like that. But if you don't believe me, solve one of the linear programming problems by tableau method that we already discussed. Go to the end, rearrange the columns in a way that you put the non-basic variables together and basic variables together, and you will see that these formulas and also hold. Try to find to write B, capital B, small b, C, B, C, and all of this, and you will see that this format is correct. So accept it from me. And also here we will have I. Always this part will become identity, because the relation of xp and xp is identity. In other words, we'll have B inverse B, which is I, identity. And identity matrix means that its diagonal is 1 and the rest is 0. And here we'll have B inverse n. We have B inverse small b. Here we'll have this. We can write it in two ways, either in matrix form or scalar form. So here, what was CB? CB was the multiplication factors of the basic variables in the cost, right? In the cost here. So here we'll have CB transpose B inverse AJ and we are talking about the non-basic variable columns, right? Therefore, AJ, if you put them together as a matrix, they become N. So that's why I'm saying that either you write it for one of them, or if I want to write them for all of them, non-basic variables at once, I can write it as N. And this, if I write for the jth non-basic variable, I can write it CJ transpose or CJ, because CJ, and if I want to put them together, I will have CN transpose. So, for example, here, if you solve this optimization problem by tableau method, rearrange the columns in order to have the basic variables here and non-basic variables here, you will have this. As you see, this is the identity matrix. This is B inverse B. Let's calculate that. Let's calculate all of these. So we have B here. We already talked about this in the previous slide. We also talked about this. These are the multiplication factors in the cost. And we also defined these, right? Now let's calculate this. So I put this together. We already talked about it. Now let's calculate B inverse. Inverse of this matrix is this. You can either use the formula, or if it is too hard for you, in the exam you can use one of the you can use a calculator. Don't worry about that. But take the inverse of the matrix, you will get this. Also, B inverse B. So you have this B inverse multiplied by B. Where is B? B is here. B is 48, 28, right? If you multiply these two together, you will get this. So this is B, this is B inverse. You will get this. See, that's what I was saying. You will have it here because of this. Also, the optimal cost will be CB transpose B inverse B. We can calculate that. So where is CB transpose? This is CB. So CB transpose will be a row vector. It will be 0, 20, 60. And B inverse B, we have it here. 24, 8, 2. So if you multiply this, it will be 0 times 24 plus 20 times 8 plus 60 times 20. Why is it happening? What is the intuition behind this? It's obvious. It's multiplication of the factors in the cost by the basic variables. So these are the optimal values of the basic variables. Do you remember? Because at the end of the tableau method, we said that whatever basic variable here is equal to this value. These are the values of the basic variables. And here we have, in the cost, we have CB transpose the basic variables plus CN transpose the non-basic variables. We know that the optimal value of the non-basic variables is 0. So this term is canceled. We only have this in the optimal value. And for XB, I just explained it. These are the optimal values for XB. Therefore, we have CB transpose the values of the optimal values for the basic variables, exactly as shown here. Clear so far? So we can also calculate these, and here we always have 0 for these. We can also calculate this by CB transpose. I think I already have explained it here, right? So here, for example, now I'm talking about this part or this part. They are the same, right? These are the columns of this. So B inverse AJ or B inverse N. So these are AJ. So we already talked about N. We already talked about B inverse. If you multiply these two matrices, you will have this. Also, B inverse B becomes I, which we have it here. We have B inverse N here too. That's why you can see this matrix here. Okay, and now you will see the use cases of these in a few minutes. Just give me a second to explain how we are forming this table. And then I'm talking about this. I can write it in all of them together, right? So we already calculated B inverse N, so we don't recalculate that. I just put it here. And this is C B transpose, and this is C N transpose. I will have this. This is exactly what we have here. We also have 0 vector here. And as we discussed in a few minutes ago, we have the optimal cost here. So this is a table, right? Now, let's go and see how we can use these for sensitivity analysis. So sensitivity analysis, as I said, analyzes how much effect some change in something has on the optimization. In linear programming, we can also have sensitivity analysis. So we can have different cases of change in linear programming. What are the changes? One change is that we have change in coefficient or multiplication factor of a variable, either basic or non-basic in the objective function. Like what? Let me bring some example. Like this. Change this 60. Change this 30. Change this 20. Change 60 to 65. Change 30 to 25, something like that. So you can either change, and this variable can be either basic or non-basic. So it can be non-basic or basic, right? Another change that we can have is the coefficient or multiplication factor of a variable, either basic or non-basic, in the constraint. So I mean A. Do you remember these were C? These were CJs. These are AIJs. You can change AIJs. Change of the coefficient in non-basic variable or basic variable in the constraints, right? Another change that you can have is that you add a new variable. So for example, you have x1 and x2, you add a third variable. So it becomes a 3-dimensional objective variable, and it will be a new variable to optimization. You add it. Or you can add a new constraint. So you had 2 constraints. For example, you are in a company, you had 2 constraints on your production. Suddenly your manager comes and says, by the way, there is another thing that we have another restriction on our production. For example, one of our investors has said that something should be done in this way, not in that way. So one additional constraint has been added to optimization, and we need to analyze that, how it affects our production, total profit, or something like that. So we can have also a combination of these changes, right? So any questions so far clear? Okay, so case 1-1. What is case 1-1? So this was case 1-1. We are changing the multiplication factor of a non-basic variable, CJ of a non-basic variable in the objective function. Okay. Because there is a difference if we change the coefficient of a non-basic variable or a basic variable. We'll see why. We'll see why. An example. The company has profits $60, $30, and $20 for the first, second, and third products. And there are some constraints like this and this and this. So we form it as this optimization problem, right? Okay. Now the company or manager says something, that some change has been applied. The company, for example, is able. The manager says, oh, by the way, we can now increase the profit of the second product to $32 or $36. Can you, my engineer, tell me whether this change is good or not? So you go and calculate how. So what is the multiplication? The profit of x2 is $30, right? They want to change it either to 32 or 36 and see what happens. So one thing, you can solve 3 optimization problems. You can solve this optimization problem once with 30, once with 32, once with 36, and see the differences. Or you don't need you don't want to solve it from scratch every time. Therefore, you can use sensitivity analysis. How? In this way. So we form the table as we discussed. We have XB, we choose some order, we stick to the order until the end. And X2 is a non-basic variable. How do we know that? Either once we have solved it, for example, you were the engineer of the company, right? You already have solved their optimization once. So you know which ones are the basic variables, which ones are the non-basic variables, which of the products have the profit and which of the products shouldn't be produced at all because they don't have any profit. Those are non-basic variables. So you already know this. In exam, either I give you the basic variables as final solution, or you should solve it once until the end and find these basic or non-basic variables, and then start the sensitivity analysis. So X2 is a non-basic variable. We have changed. Why? Because X2 is not here. X2 is here. We have change in CX2 in C. Therefore, we have change in Cn. It's a non-basic variable. We have change in CX2. Okay, where does Cn appear in this table? So we don't have Cn here. We don't have Cn here. We don't have Cn here. Don't have it here. Don't have it here. It's always 0 here. We only have it here. So the only difference that it applies is this part of the table. Let's see how we can analyze it. So let's calculate it. So as I'm only talking about one of the variables, therefore I use this rather than this. Rather than all of the non-basic variables, I use only one of them. Therefore, I write it in this way. So this is B inverse AX2 only. So we have, this is the only column on the column of AX2, the column for X2 in B inverse N, right? The column associated to X2 and with this order, with the same order. It means that the first column, according to this order, it is the first column of B inverse N. So, and also I have CB transpose, I have CX2, C this is only changing, or this is only changing, right? Now let's write it 30 plus delta. We don't know the delta. We want to find the delta. 30 plus some delta. Delta might be positive number, might be negative number. We might increase the profit, we might decrease the profit of that. So if we multiply this, so delta is a parameter. If we multiply, we will have this. So we'll have 5 minus delta. Now, what if this value is non-negative? It means that we shouldn't continue the table. What was the termination condition in the tableau method? It was when we don't have any non-negative value. We always have non-negative values in the 0, right? And this is the 0. This is 0, don't care. And only we are caring about here right now. So this, we know for the other non-basic variables, they are already non-negative because the optimization was already finished before. So the only change is here. If it's non-negative, still, it means that if delta, rearrange this, if delta is less than 5, it means that if we decrease 30, decrease it, or increase it at most to 35. At most to 35. There is no change in optimization. We don't need to continue optimization because the termination condition of linear programming has been already satisfied. Clear so far? Right? Clear? So we can say to the manager, if you increase the profit, if you decrease the profit of this X2 or increase it at most to 35, you don't need to do anything. Do it as before. However, if you wanna So for 32, that's fine. Doesn't change anything. However, if you increase the profit to 36, I need to recalculate. I don't calculate from scratch. I continue the table. Because I don't have enough time to go and solve from the scratch. So how do I continue the table? I replace, so this was the previous 0. Now I update it. And why is it -1? You can calculate that this again with 36. So replace this 36 and you will get -1. So you have -1 rather than 5. Now these don't change because they don't have CJ anymore. Only these changes, right? Now let's continue as before. Assume that we have this situation in the tableau method. Get the most negative value. This gives you the pivot column. Do the mean test. Gives you the pivot row. Do the elementary row-wise calculations in order to make this 1 and the rest 0. This is exactly what we have done. This is 1. And finally, we'll say, oh, by the way, now it has become all non-negative. So we only needed one more step of optimization with this change. Maybe if it doesn't become non-negative yet, we continue the table. This change might require us to solve 5 more iterations, 6 more iterations. We go until we reach all non-negative values for the 0, right? This change only needed 1 iteration more. And we have these S1, X3, X2. And by the way, we replace the name of X1 with X2 as before. Now you see this change made X2 a basic variable. And X1, which was a basic variable before, has become a non-basic variable now. So we have these optimal values now, and C has increased. C has been changed. Has C increased or decreased? It has increased. You can say to the manager, if you increase the profit of X2 to $36, our total profit will be increased. And also, we should start producing X2 and stop producing X1. Right? Because X1 it will give you the 0 profit. We don't care about that anymore. Until now, we were producing X1. We were producing X1 and X3. Now, from now on, we should produce X2 and X3. Is it clear? Can you give me feedback, please? Yes? Okay, great. Case 1, 2 of change now. What was case 1, 2? Now we are changing CJ, the multiplication factor of a basic variable. Basic variable in the objective function. So assume this problem again, the same problem as before. The manager says the company is decreasing the profit of the first product. The first X1, do you remember, was a basic variable in this problem. To 58 and 30. So it was 60. Now we are changing it to 58 and to 30. What do you recommend to the manager? Let's see. Okay. In this table that we have, where do we have, so what we are changing CB, right? We don't have CB here, here. We have it here. We know whatever CB we choose, this becomes 0 for now. So we also have CB here. So these two, we should take care. And here, let's see. So I'm recalculating this. Now, as I have CB here, I should do it for all of the non-basic variables, not just one of them, because CB is here, right? At that time, I was talking about, in the previous case, I was talking about one of the non-basic variables. So I only was working on one of them. Now, this change of CB is affecting all of them, all of the non-basic variables. So I have to do it for all of them. Now I put this 60 plus delta here, Previously it was 60, now it's 60 plus delta. Cn doesn't change as before. We will have this. It will be parametric, right? And in order not to continue the table, each of these should be non-negative to satisfy the termination combination of the tableau method in the linear programming simplex algorithm. So these should be non-negative. This gives me this. This should be non-negative. This gives me this. This also should be non-negative. This gives me this. What is the intersection of these three? Is this, right? These three conditions. Delta should be -4, between -4 and 20. And what is CX1? So CX1 was 60 plus delta, right? Here we had it. So it means that CX1 should be between 56 and 80. Why? Because add 60 to the size of this inequality, and you will have this. So it means that you will say to the manager, if you change the multiplication factor or the profit, here is profit, the profit of the first product from $56 to $80, nothing changes as before. However, so for example, 58 is in this range. I don't need to change. Nothing changes. It will be the same. However, if you change it to 30, I need to recalculate. I need to continue the table. How? Okay, let's do it. I'm calculating this again. Now it's 30. I will get these. Also have CB here, right? I had CB, effect of CB in these two. I had effect of CB in these two. Now I'm calculating these two. So the cost also, exactly wherever I want to start continuing the table, even the cost has changed because of the change of coefficient of the basic variable. Because the base you are changing for the basic variable, that obviously changes the cost too. So the cost has been changed from 280 to 220. Also, these have been changed to this. So this is the updated. Again, as before, we continue. We choose the most negative value in the 0. This gives you the pivot column. Do the mean test, get the mean, and get the pivot row, and do the elementary row wise calculations. These are the calculations. You need to do it for 2 steps. And finally, you'll say these have become all non-negative. And what have changed? What changes do we have? So here, for example, so S1, X3, X2. What were it before? S1, X3. So before these were the basic variables, S1, X3, X1. Now we have S1, X3, X2. So see, X1, which was the basic variable, has become non-basic, and X2, which was a non-basic variable, has become a basic variable. And the cost also has changed from 280 to 272. It means that it has been decreased. So you will say to the manager, if you change the profit of the X1 to $30 from 60 to $30, our total profit will be decreased from 280 to 272. Is that correct? So, and by the way, there is another change too. You should tell to the manager, we should, if we want to do that, we should stop producing X1 and start producing X2. Clear? So case 2.1, what is it? Change in coefficient of a non-basic variable in the constraint. So change Aij in the multiplication factor of the variable, which is non-basic variable, in the constraint. I think you got the idea of the sensitivity analysis. You will see in the formula of the table that we discussed, you will see whatever you are changing, where does it change the table? And you will see what should I do in order not to continue the table. So this gives me the range. And if the range is not satisfied, there it means that I should continue the table. Then I will continue the table and I see the changes and I will report it to the manager. So this is sensitivity analysis. So I think it's so simple. The idea behind it is this. Now, an example. The company is changing the resources for X2 as this. This, and this. So let me see. Yeah. So what is the difference? Let me see. Give me a second. Yes. Compare this and this. This was before. This is after. So the multiplication factor of X2 has changed. Also, the company is changing the profit of the product to 50. So here in this example, we have two changes. I want to show you how we can have a combination of changes, right? So the company is changing the profit of the product of X2, right? X2, I think. Yes, X2 to 50. It means this. So we have a combination of changes now. I want to show you how you can handle that. Again, you will see in both cases how they are changing. So we have changed. XB was it X2 was in a basic variable? No, it was a non-basic variable. So we have change in CN. We also have CN. We also have change in AIJ for non-basic, for N, in N, right? So we are changing, we should care about this 0 especially. So we are changing this. We are changing this. We are changing, where else? Can you tell me? Yeah, I think we are changing this here. So we are changing CN, also N, both of them. Let's see, let's calculate this. So we have, this is B inverse. This is AX2, which has changed. We have changed here, right? We also have, this is CB2, CB transpose. CB hasn't changed. CB hasn't changed. Also, I have changed here. No, I don't. Sorry, I don't have. Let me see. Let me see. CX2. I think this must be 30. If it must be, I will correct it in the slides. So you will calculate and see that it doesn't change the optimal solution. So it doesn't change the total profit. If that would become negative, then we had to continue the table again as before. So whatever change you have, either a combination of changes or one change, you see where do we have changed in this table, especially the 0, because the termination condition depends on the 0, and in the 0 we should have all non-negative values. If it doesn't satisfy that, then we need to continue. I think you got the idea. Let's go to case 2.2, and I think 1 or 2 cases will be remained for the next session. So so change of, for example, coefficient of a basic variable in the constraint. So Aij for basic in B, right? Not in N, in B. Okay, an example is that for X1 we are changing the resources. Let me see. So here we are changing 8 to 5. Also we are changing 4 to 5. Also we are changing 2 to 1. We are changing all of them in the all of the constraints. Assume that the investors want some change on the restrictions in the company. What is your recommendation? Let's see how it has an impact. Also, okay, X1, we knew that it is a basic variable. Okay, and we are changing for X1. So it means that we are changing B. We're changing B. Here we have a change. Here we know it's always 0, so we don't care. Here we also have a change. Okay, now let's see. So here, CB transpose B inverse N. So we have B inverse, this is B inverse, this is CB transpose, and this is N. And this has changed. X1, B. This was previous B. This was previous B. Now we have changed in AX1 in B. And where is AX1? Because of this order, it's the last column. It's the last column. So rather than 842, we have 551, right? Now we calculate that, and Cn doesn't change. Cn doesn't change as before because these are the multiplication factors of the non-basic variables in the objective function. So it doesn't. We only have change here. Now, if we compute it, if any of the values become negative, we should continue the table. Otherwise, the total profit does not change as before. As before. Let me see. Yeah, I think let these two last cases, several last cases be talked about in the next session. And in initial minutes of the next session, we will cover the very last cases of the sensitivity analysis. Again, the idea is the same as before. Afterwards, we'll go over the KKT conditions, Kairos-Kontaker conditions, because the Kairos-Kontaker will see that is the backbone of many of the, almost all of the optimization algorithms. And afterwards, we will see some examples, and we'll see Lagrange multipliers and Lagrange multiplier method. And afterwards, we go and see the first order methods, such as gradient descent, stochastic gradient descent, and these areas. And we'll have a lot of fun. We'll have a lot of fun. And I think if we have time, I will go over some of the neural network stuff too with you. I will show the code and how you can work with that, so you can understand how cool it is. And I think, yeah, we'll have a lot of fun. And afterwards, in the next sessions, I think the session after the next session will be reading week, if I'm not wrong. I should take a look at the calendar. But if I'm not mistaken, the week after the next week might be reading week, I'm not sure. And then we'll have a midterm session. After the midterm session, we'll continue that. But the first session will, with the next session, we'll definitely go over the KKT conditions and some of the first order methods. Okay, any question?
Hi, Ben. Actually, I wanted to ask that like the table that we use right now for calculating, so we need to remember the formula for it to make calculations?
See, if you wanna solve the optimization problem, no, you shouldn't. You should solve it from scratch. Why? Because for that formula that you said, whether you need to remember or not, you should know which of the variables are basic and which are non-basic. You can't predict which ones are basic and which. So if you have an optimization problem, you need to solve it from scratch, because you don't know which ones are basic and which ones are non-basic. However, if you somehow know which ones are basic, for example, in sensitivity analysis, you already have solved it once. For example, you are in a company, you already have solved it once. It's in your documents. You don't need to solve it from scratch again. You will continue the table. You get my point?
Yes, I got it. Okay, thank you.
And it's good to have the formula in mind for sensitivity analysis and these things. And you don't need to memorize that. If you know the intuition behind, I briefly talked about the intuition behind the table. I think you will figure it out how you should form the table. Yes. Any other question?
So sorry. So like, when was the midterm again?
The midterm, I think it will be the week after the reading week, and I think it will be, if I'm mistaken, please let me know. But I think it will be February 28th, right?
Oh, okay, okay.
I'm not sure.
Yeah, that's
If
I
that's
think we talked
correct.
about last time. Yes,
Okay.
sorry.
Yeah,
Yeah,
that's
reading week goes from the 20th to the 27th. So
okay.
the class after reading week is the 28th.
Oh, yes. So it means that we'll have the next session. We'll have the session after next session. So next session will be February 7th, and the next session after that will be February 14th. February 21st is we don't have a class because of reading week, and February 28th you will have a midterm exam during the class time.
Okay.
Okay. Any other question? And before we leave, just could you please let me know your feedback so far? How was the course? Did you enjoy it? Did you find it interesting and useful? For me,
it's an interesting.
It's interesting.
Yes.
Okay, great. Because for me, the most important thing is that you enjoy the course and you learn in the course. Okay, great. I'm happy. I'm glad that you have found it interesting and useful. And please be aware that I'm sure that this course will be very useful to you either in academia or in industry. So when you have this knowledge, you will gain some confidence on what you're doing in both industry and academia. We are also showing a lot of examples, practical examples in industry during the course. For example, I'm saying that if the manager says what you should do this. So we are covering both cases for both use in industry and academia. If you have any feedback, you can let me know here or offline. I will be happy to apply your feedback. Any other question or feedback? No? Okay, thank you very much. I think we can conclude the session. Thanks and have a good night. Thank you.
Good night.
Thank you.
Thank you.
Thank you.
Thanks, Ben.
Bye.
Thank you. Thank you.
Thank you.
Thank you. Thank you very much.